Okay, I'm going to test the audio here by listening at the other machine. I have to apologize about today. I am feeling better than I was this morning, but I'm quite a bit off today. Let's see if I can get the audio to come through. There we go. Okay. Now I'm back on this side of the room. Let me kick the audio up over here. Let's see. All right. Okay. I'm testing 1, 2, 3. Let's see. Let me listen to it over here. Okay. Now I'm back on this side of the room. Let me see. All right. Okay. I'm testing 1, 2, 3. All right, I'll start in about 5 minutes. All right, so I'm going to go ahead, even though it's 10:59 up here. So it's almost that time. So we talked last time about these different angles, and this is a completely different approach, something he calls transverse and azimuth angles. So let's compare the difference here. Imagine, if you will, it's high noon and the sun is directly overhead, and the rays of light are coming down, and this is your vector. So this is what you would see as kind of a shadow. So this vector is a shadow of the vector that you actually have. Now, believe it or not, you actually have this vector, this component. So it is in a square box here. This component in the Z is through this angle here. So imagine that all you're doing now is you're looking for this component and this component. So you have what he has here, a lightly shaded blue. Here's a little darker shaded blue. These are two different planes. So from this plane, you just see a triangle here. Now, it doesn't look like it, but if you stand over here to the side, you will notice this is 90 degrees. Now, he is giving us this angle. So in this particular case, AZ, the value of AZ, the length of AZ, is equal to the length of A, the length of this vector, times cosine of an angle. Now, technically, let's get rid of a few things. And technically, if I were to draw a line from here to here, and if I were talented enough to copy that, I should be able to take that thing and drop it right there, and it's the same thing. So essentially, this length, this length is actually the same as the length of this vector down here. So, that being the case, the length of the A prime vector down here, or the shadow vector, is equal to the length of this whole vector times the sine of that same angle right back here. So if you back away from what I've written here and you look over to the right, this is what you see. You see now in his textbook, these bold symbols are vectors. The non-bold symbols are actually scalar length. So in fact, what I've written, in other words, this is actually the same as that. But this A is the scalar length of, of this A here. So realize over here you're dealing with the scalars. You're just looking at lengths here. Now, you also see the shadow vector. The shadow vector sits right here. Now, okay, so now that you've established this and you understand the length of this vector, now you start working in the plane. So now you're like, I have this vector. It's a shadow vector, but I don't care whether it's a shadow vector or not. It's a vector that lays in the XY plane. Now, if I look at this triangle that he's presented right here and say, well, that is a plane that's actually laying exactly in the XY plane, I can determine this length of this side, which is equal to that. So AY, the length of that vector, is equal to the length of the shadow vector, which is this, times you're moving through the new angle down here. So you got two angles. Once you've worked your way through the shadow, you don't need that one anymore. Now you're looking at this length. Now let's find this length, and then it's nothing more than the shadow vector again times the cosine of that angle. Okay, so here you go. So if you look at it, again, this little lowercase means the length. I wish they would do it a little bit differently, but that's the length of that vector. This is the length of that vector. This is the length of my shadow vector. This is the length of the shadow vector. So then what he does is he says, hey, wait a minute. I have the length of the shadow vector right here, and so I'll just insert it right here, and we'll go on from there. So that's pretty much it. And then what you have, and this is kind of weird, you have the vector A written in this particular form. Okay, now I realize before we had alpha, beta, and gamma. Now we have just two angles, those two. And so you have a component that's two sine, or a sine times a cosine for the x, a sine times a sine, and then just a cosine. Now, there is a relationship between this and this, but that's okay. Okay, so addition of Cartesian vectors, that's simple. You just add the components, and then you're off doing problems. So let's just head off, pick up a problem. I do not like these preliminary problems, so I'm going to skip that. If you have an older edition of the book, they don't have those, and I don't know, they didn't seem to have done a fairly good job with those, in my opinion. But so here, let's look at the setup here. Okay, so when you see this, you see two different color shadows, two different color triangles. You're looking at the two angles. When you're looking at this, it's basically the angle between that vector and the coordinate line. So let's go through each one of these. First, let's just pick, all of these are about the same. Let's see. The one complexity that exists in these two that doesn't exist in here is that this is in the positive XYZ, and this one is not necessarily in the positive XYZ. So this extra complication means I'm going to sort of focus on this one, I think. So let's take a look at this one. Grab it, head over, drop it. Drop it. I don't know what happened there. It ended up dropping itself. I don't know. Anyway, so again, we're back at this point where we're looking at the shadow vector. Okay, so we drop a shadow right here. So what I'm going to do is I'm going to look after, or try to find, the length of that vector. Likewise, this will form a plane, and this one just so happens to be visually at the point where we're standing here looking straight at it. For example, this other one, well, this one's kind of that way too. Often they're not, so there's an interpretation here. So we'll have to find one that's a little bit odd in a minute. So let's take a look and find out if we can find that, and I'll just call it A. It's nothing more than, okay, this is the 50 pounds, and it's a cosine of 45. So I'm going to carry the numbers, but if I'm going to do that, I'm going to start relying here. So it's 50 now times cosine degree of 45, which is the same thing. Whoops. The same thing as 50 divided by the square root of 2. 35.355. So it's 35.355. Now, it turns out, if we want to know the vector here, here's what's interesting. Okay, I'll go ahead and do this to indicate that it's an actual vector here that we're looking for. This component, believe it or not, is I guess that's called f. This vector is called f, so I'm going to say f, the z component, and I wrote y. The z component is going to be 50 pounds, and technically, okay, I'll do sine of 45, but it turns out it's the same value. So I have that. That's a given, and I'm okay. Now what I'm going to do is I'm going to move it over to the side here, because I'm going to use this picture to keep working on the x and y components. So now, okay, so I'll go back to this one. So now I'm looking here. Let me zoom in. I'm looking for the component this direction, which is going to be here, and the component in this direction, which is going to be here. I don't know which one you might be interested in first, but I'm going to pick that one. So that's going to be the f in the y direction is going to be 4/5 of the length of this thing, of the length of a prime or a shadow, whatever you want to call it. So it turns out that's 4/5 of the same 35.355, and times 4 divided by 5, 28.284, I think. 284. That's great. So now that I have it, I really should now focus on trying to find that value. Okay, so the fx, now here I have to be careful because the positive direction is this way. This vector is going the other way. So I'm going to go ahead and drop the minus sign right there on it. And it's of a ratio of 3/5. 3/5 of the length of that shadow vector that was dropped there, or minus 3/5. That is 35.355. And so fx is going to be slightly smaller, 21.213, if I'm not mistaken. Now, what I'm going to do is I'm going to write this vector out. So the vector f looks like minus 21.213 I plus, where did my, okay, there's my other one, 28.284J plus this length, which is 35.355K. Now, at this particular point, we could probably say we've accomplished what he wanted us to accomplish. However, let's go further. Okay, now that I have this, can we find the unit vector in the direction of F? For example, it says 50 pounds, right? It's a 50-pound pull on this rope here. It's obviously some sort of rope looking thing. So in this rope that we've got here, we could actually draw a vector of length, say 1. That's a unit vector. Now, unfortunately, I was calling it a base vector before, and that's not completely true. But, oh, yeah. Word of the day. Here we go. Let's do a stop here. Sorry about that. Sometimes I will forget, and so word of the day equals, okay, bucket here. Yeah, let me go. That's the wrong place. Here it is. Okay, so I'm going to just put my own in there. And like I said before, it doesn't have to be completely upper or lowercase. Oh, and you got to hit the submit. Now I should get, I get the lights. I've seen that commercial about the robo. Okay, am I going to get an email? There it is. So there's my word of the day. Came back to me. You should get this back to you as well when you get it. So here, let me get it off the screen now. Go back to it. So unit vector, back to the point here. Trying to find a unit vector which points in the direction here. I'll do it this way. Trying to find the unit vector which points in that direction. A vector that points in that direction which has a length of 1. How do we do that? Actually, it's pretty simple. The first question is, I'm going to ask a stupid question. What is the length of F? And now what I'm going to do is I'm going to make use of, I believe, Octave or MATLAB to solve it. Now, this will be kind of a semi-lesson in MATLAB. So if I list F as a vector, I can list it in an interesting way. The way I can list it is minus 21.213, but let me put a square bracket in front of it. 28.284 and 35.355. And it looks like I have 3 components there. Turns out there's a thing called a norm that is associated with that. And of course, the norm is the square root of the sum of the squares. And what you find out is it's exactly 50. Okay, well, why would it be 50? Well, because that's what it's supposed to be. So now, if I want to know a unit vector that's going in that direction, what do? I want it to go in the direction there. I basically just take the vector F and put it on over the length of F. So it's just minus 21.213I plus 28.284J plus 35.355K. And divide all that by 50. Okay, so let's see if we can do that real quick. Okay, so now I'm going to call it, wait a minute, here, let me delete all this. We call it U for normal, U for unit vector, and I'll put a little F, I don't know exactly why, but F divided by the norm of F, which is the same thing as this, And I get these numbers. Okay, so let's see if I can copy these down. Minus 4 or 0.424 26 I 5 6 5 6 9 J. This is my unit vector in the direction of F, plus 0.70711 K. Now that I have that, what am I going to do with it? Okay, well, someone could ask the question, what is the angle between this vector? Let's see if I can make a better copy of it. Let's see if I can make a copy of it. Do a copy, and I'll sort of drop to maybe right here and drop it back. So now somebody wants to know the actual angles related to, okay, I don't know if I'm zooming in on this or here. Okay, you can make it larger, so I'm going to make it larger. So now somebody wants me to give them the angle between this vector and a vector that's going this way, and a vector that's going this way, a vector that's going this way. So what he's done is he's called this one alpha, he's called this one beta, he's called this one gamma. So how do we do that? If you look back at the text, it becomes pretty apparent. And let's look back at the text and see if we can see exactly how to do that. I know this looks a little hideous right here, but let's just stare at this for a minute. This is exactly what I did. Is I found the unit vector. Mine was an F over an F, but that being the case doesn't really matter. You'll realize that's equal to the cosine of alpha, cosine of beta, cosine of gamma. So how do we do that? In MATLAB, it becomes pretty simple. Whoops. Okay, let me see. Go back here. Okay, I have a UF, right? So I can do arc cosine degree of simply the UF vector, and it does it on each component. So I get alpha equals to 115.104. I get beta, which is the second term. So this is alpha. This first one's alpha. The second one's beta. Third one's gamma. 55.55, and gamma is equal to 45 degrees. Now, let's make a quick look at this. Okay, wait a minute. If we stare at this, before we realized we had a triangle that looked like so. We had this triangle, and it went back and went like this. So in fact, this is 45. That's got to be 45. So in fact, that makes perfect sense. This actually matches the angle that we got before. This is a little bit different. Now think about this. Let's look at beta, for example. So I take this triangle. Let's imagine that it was close, or say it was right in this plane. It gets moved back. So this angle has to be slightly more than that 45. And then the 115. Well, the 115 is because if I swung this to that plane, so in other words, if I swung this, if I took this, and it took a vector that was in the plane, I could swing that back, and swinging it back, I would get the 90. So if I push it back behind here, it's got to be greater than 90. So in fact, I feel pretty comfortable about the three numbers that we came up with. And so, this is this is basically everything that you're going to have to do. You're going to have to either take angles and run them backwards to find the unit vector, and then run them against against a length or a force there, and then come up with the force vector. Or you're going to be given two triangles like this that are slightly different colors, and you'll be able to recognize this plane, this triangle is sitting in this XY plane, and this triangle is not, it's perpendicular to that. And so you get this projection vector that's right here that's projected. Just imagine high noon, the sunlight projects this vector right here onto the ground, and then you're working off of this vector to get these components. And so that all the problems look the same if you look at them. There might be certain things that he's trying to get out of you. For example, one particular example is if I was given like 111 and 30, how do you find that? And it turns out you're limited by this. You can't be given 111 and 30 degrees, and this can be anything. And the reason it can't be is because of this. There's a relationship between them all. And that relationship sits right here in this funny blue box, which we'll circle in red, and that is this, that you are forcing this vector to be a length of 1. Why do you want it 1? Because then I can just multiply that vector times, say somebody's pulling on the rope and somebody says it's 50 pounds. So there's your vector. So there's your force vector. But say it's 150 pounds or 450 pounds. This didn't change. The direction didn't change. The force did. And so you have a relationship. If you're given this and this has to obey the relationship. So past that, there isn't anything else. Let's see. Let me find some. Okay, those were the fundamental problems. Let me go see if I can find. Okay, here's a typical case that I was talking about. Let's find that. Okay, I think I hit the, no, I didn't hit the S. He says, drop it right there. So he wants to know the vector. Okay, well, F is going to be equal to the value or the force, which is 80. So it's 80 times the unit vector. Well, the unit vector is basically, here I'm looking over at that. So the unit vector can be determined by, or is determinable by this, but you're only given alpha and beta. You're not given this gamma. Oops, gamma looks like this. Yeah, anyway, I'm having trouble with my hand for some reason. So here's the deal. Cosine of 45, which is this number, and you square it, plus the cosine of 60 squared, plus the cosine of whatever that is, it's got to equal 1. I want my unit vector to be unit vector of 1. So what do? Cosine, inverse cosine. How about doing it that way? Well, first let's do it this way. Cosine is equal to, and I have to square it, or square root it. And so I end up with gamma. And so what I'll do is I'll turn around and do this. Whoa, hang on, I lost my pen. is equal to gamma. So let's see if I can put that in the octave. Oh, that's the wrong. Okay, go back to here. And then go here. Okay, so let's see if I can put that in. Oh, but I've got the wrong thing under me. Here we go. Okay, so come up here. Okay, so arc cosine in degrees of square root of 1 minus cosine degrees of 45. Gonna square that minus, ooh, it's all cap. Okay, a cosine degree. I think it wouldn't work if I was doing that. Square root of 1 minus cosine degree 45 square root minus, I'm squared, minus cosine degree of 60. Square that, drop that off. I think I have balanced parentheses. Uh-oh, I don't have balanced parentheses. I have to hit another parentheses and enter. So it says 60 degrees. This is kind of there's a rare one like that, in which the things come out to be integers. So now that you have that, you have f is equal to 80 times cosine of alpha I plus 80 times cosine of beta j plus 80 times cosine of gamma k. Or you might as well take them out now and put in the 60, the 45, and then another 60. Let's play around for a second now before I calculate here. If I were to shift, let's say I were to shift this vector towards the y-axis, and say I made that 44, and this was still 60. Let's say this was still 60. So I'm essentially rotating this vector around this axis. So if I drew it back, how does it affect that? So let's take a look. So I'm drawing it back, and instead of 40, instead of 45, somebody's going to tell me that needs to be 44. So what happens then? In fact, this angle picks up. Let's do something interesting. Let's see. What if I drew it all the way back down to the point where it was 0, where this essentially is drawn down to the point where this is 0 and lays on that axis. And there it is. Guess what? You can't do that. Why can't you do that? Okay, hang on. Oh, wait a minute. Because if you drew that down, there's a certain point in which you're not going to be able to put, there's a certain point where you can't put that in this, on that axis. For example, here's what I mean. If I drew this beta to 0, let me redraw it. Okay, so if I drew beta to 0, that means it's sitting on this axis. That means automatically that's 90. So already you're confining yourself. So if that were 90 and this were not, this would have to be 90 as well. So you can't just arbitrarily change these things. They are all interrelated. The three angles are all interrelated, of course, through that equation that's at, oh, it's back up in the page. So you can't just move things at random. There is a relationship between alpha, beta, and gamma. So now, if you really want to find the answer, what is interesting is you can do, I'm going to do this. Do a clear everything out and clear the screen. Now I'm going to put in here angles, and I'm going to put in my 3 angles, which were 60, I think 45, and another 60. So there's my 3 angles. Now I'm going to do something bizarre. I'm going to say my unit vector is equal to cosine in degrees of the angles. And what you'll find is it took the 60, and the cosine of 60 is that. The cosine of 45 is this. Cosine of 60 is again that. And now what do I do? Well, I can take the unit vector, which is already defined, and multiply it times 80, and I get 40, 56, and 40. So that's the actual vector, 40, 56, and 40. So if you want to, 40i plus, I've already forgot, but I think it was 56.569. J plus 40k. And that's pretty much it. Now, you could say, well, I want to go back and find the azimuth and things like that. But generally, once you're given things this way, you generally don't go back and find a vector's components like that. I'm not doing a good job of the drawing here, but in other words, this would be the shadow that would be casting. This would be the shadow on the ground, and these are the components here. So generally, you don't go back and ask those kind of questions. Let me see if I can find anything else that is quite complex here. Well, I guess the next complexity is adding things together. So up until this point, back in here, these are all single vectors that you're determining components to. Now you've got single vectors with an adjoining vector, with a added vector. So let's see, got 37, I'm at 1137. Let's see, what can I find here that's interesting? What's the most interesting problem? I'm not sure I can find the most interesting problem. I'm not sure there is an interesting problem. So here, let's move on, and I'll use this last few minutes to cover position vectors. Okay, so it's great to actually get angles and do things like that. However, it's more common in practice to do things this way. So if you had a position vector, you could find information off of it. Here's what I mean. And this is probably better to show a typical example. So here he's got a coordinate system. He has 2 funny looking ropes here. And he says, hey, this rope has a tension of, does it have a tension? Anyway, rubber band has a tension of something. So what I need to do, I'm interested in whether it's going to pull this end out of the wall. Now, I could be equally concerned with the upper end, but I got to pick one of them first. So I'm interested in this. So I'm interested in, let's say the tension of the rubber band's 100 pounds. So I'm interested in finding out the force vector on A of the rubber band. So it's 100 pounds times the unit vector going from A to B. So how do I find it? Well, that's pretty actually simple. So if I draw a vector to here, I can say this vector, it goes, okay, so let's go R to B. It goes backwards in the 2. I go backwards 2 meters minus 2i then I go positive 2 meters, 2 meters in the J, and then I go up 3 meters. Okay, so I found that vector. Now I'm interested in finding the vector that points to here. So I'll just call it RA. Okay, so the RA, how do you get there? Well, let's first transverse out the x-axis, which it looks like it goes 1, 1, I, and it doesn't go any J. And then it goes downward 3, it goes downward 3 to get to that point K. Now, let's really look at what we're trying to find here. So I'm going to get these other ones off the diagram. And I'm going to say, hey, really, let's look at this. What I'm trying to do is I'm trying to find this vector. So here's my vector that I'm looking for, which I'm just going to call it F. And I'm going to say plus, okay, wait a minute, plus RA. I better not call it F. I better call it something else. I better call it, how about I call this vector capital R? So capital R. So if I add this vector to this one, I should get the B. RB. So it's just vector addition. But now what I'm interested in really finding is this vector. So if I come down here, I'll say my R vector that points from A pointing to B. So maybe that's what I should have done. It's pointing from A to B is equal to RB minus RA. Well, you already know how to do that. Let's see. You go in, you take RB, which is 2 minus 1, that'd be minus 3. I take the B, 2 minus A, oh, that's easy, plus 2J. And then take the B, the 3 minus this, okay, minus plus, it becomes 6K. So that is the vector A that points to B. Now that I have that, guess what I can do? I can find the unit normal. Now, let's see if we've successfully done that. If you look at this vector, he's drawn right here. He's called a capital A, and it's the same thing that we have here. Minus 3 plus 2 is 6. So my unit vector is, of course, equal to RAB over the length of RAB. And I think that length is 7, if I'm not mistaken, but I might be wrong. Yeah. There's something convenient that he does in this course, and that is he makes everything kind of a similar unit, which is annoying, but yet, I guess, okay, in some sort of strange sort of way. But yeah, it's okay. It's all right. So the actual unit vector is 3 over 7, 2 over 7, and 6 over 7. Now, to carry this further, okay, well, now then what he does is he says, I'm going to take, I want to find my alpha, my beta, and my gamma, and that's fine. But he doesn't go to the next step, and the next step is, hey, well, what if that rubber band was a tension of, let's say it was 70 pounds. Yeah, this is what he does a lot of in the book. Okay, hang on. Let's say it's 70 pounds. So the tension in that rope or rubber band is 70 pounds. Well, then what is a vector? F is equal to 70 pounds times U. Well, the 7 and the 10 cancel, so it's equal to 30 I plus 20 J plus 60 K. And that's what he's doing most of the time. And he does this now. You can tell this book has been written years ago and has gone through many different cycles, because it'll come up with integer values where that's great and that's true, but if you just shift this one, or if you had a 3, and a 6, it's not going to be an integer value. There aren't very many cases that you can get an integer value, and he spent a large amount of effort making those come out that way. So don't get the false impression that everything comes out to be an integer, because it doesn't. Okay, now he's talking about force directed along a line. Okay, what is he doing? Well, he's saying multiply that 70 times the unit vector. That gets you the vector force. And so here's a typical case. Okay, again, all right, so it turns out that 12, 8, and 24 give you a length of rope, an integer length of 28. So look at it from this perspective. The R vector, you go 12i, let's see if I can start where the guy's hands are. And let me switch a color so you can see it. So I go 12, then I go, well, wait a minute. He's wanting to know so there's two ways to be concerned about. You're concerned about this, or you're concerned about this. Looks to me, he's concerned about it pulling out of the wall. So he goes, and it looks like I'm going to have to do this along a different direction. So I'm going to start with this. I'm going to move down, and that's 24. Why is it 24? It was 30 minus 6. And then I move, and I'm moving down. I'm moving in the negative direction. Then I'm moving back in the negative, this being positive, 8. And then I move out towards the guy's hands, 12. So this vector is actually pointing this way. Okay, so he goes down and finds it. It's 28. And then he takes his components, divides it by his length of the vector. Then what does he do? Well, he's got the 28, and it just so happens if you throw 70 in there, you knock out some values and you end up with the integer forces again. It's just the way things are, But these will rarely in real life end up as integers, and that doesn't end up as integers often. The next thing he does is he wants to find the alphas. Well, what you do is you take the alphas come from your base vectors, and you take the 12 over 28, that goes in here. The minus, you got to keep your signs with it, minus 8 over 28, and the minus 24, over the 24, gives you your angles. When you end up with a minus sign, you're going to get greater than 90 here. If you forget your minus signs, you're going to get the wrong value here. It's going to be less than 90. So I think what we'll do is I'm going to have to send you an email about what's going on next 2 class periods. The next one, I've got a scheduled meeting during, and so I'll send you some information about that, but I may still try to do a live stream on it anyway. So be watching your mailbox, your email box, or whatever you want to call it, for an email coming to you about the next 2 class periods. I'm hoping to get back in sync normally next week. We should be back into a normal sync. We will still do virtual Fridays, and so with that in mind, I guess I'm done. So let me take a look over here and see if there's any sort of comments in the comment box, or I'm sorry, it's called the chat box or whatever. I don't see anything. So I guess we're just going to call it good. And watch for your emails coming at you.